Now let us see. Next is, okay, dust is ignited. Now this dust is a layer dust which is ignited. Now we are going to talk about flames in which dust are now dispersed in gases or air. Obviously, I have air plus dust mixed. So that means there is a gas and there is a solid particles. Okay, so it is heterogeneous in nature. There are more than one phase. Dust flame. So this is supplied to a burner, or it is entraining. Dust is entrained by the flowing air and it ignited as it goes. Now let us take a flammable dust particle which interact with hot air or gas ambient. Then what happens? The dust particles will pyrolysis first. Pyrolyze, and gaseous fuel come out of that and char will be formed. If there is a charring fuel. If it is not a charring fuel, then it will just leave some residues, etc. Now the charring fuel, char will be formed, carbon from ash, and that can also get heated up and react with oxygen as a surface reaction. Okay. Again, that means that the rate limiting step is basically the pyrolysis step, where the heat is required. First of all, the dust particles will take heat from the ambient, get heated to a temperature which is close to pyrolysis temperature, then pyrolysis gases are released. Then the pyrolysis gases can contribute to gas phase combustion. Again, more heat transfer is required for char to get heated up if it is a charring fuel, and so on. So whatever you have seen, the solid fuel combustion will hold good, but here the main advantage is the particles are very, very small. That means the rate at which heat and mass transfer occurs are very high. The pyrolysis gases or volatiles mix with oxygen from the atmosphere, and gaseous products are formed. So that there is homogeneous phase reactions. Homogeneous reactions, gas phase reactions occur. That will lead to more and more heat release. Then if it is a charring fuel, as I told you, the char gets heated up, and if oxygen comes to the char surface, then oxidation reaction at the solid surface occurs. So the heterogeneous reaction. So this is homogeneous. Surface. Now, commonly dust flames are seen in coal mines, because when you process the coal, lot of particles, fine particles are produced. Now these fine coal particles interact with air or mixture of, see, in the coal mine there are two things. Coal dust is formed, then methane also is generated. Methane is generated in a large quantity, and if there is air entrainment into this mine, then methane and air can form a mixture easily, and the coal dust can be entrained into this methane air mixture. So this is one of the things. Then such a fine dust fire can also occur in chemical industries, metallurgical industries, and pharmaceutical industries. Basically what should happen is a combustible cloud should form, where dust and some hot gases or air should be formed, which will lead to dust combustion. Okay, now for the dust flames, there are several controlling factors. Dust layers deposited in mines, coal dust for example, surfaces of mines, or industries which can handle organic or non-organic dust which are deposited over machineries. Okay, now if there is a flow, these dust particles are fugitive. They lift, get entrained into these gases and mix well with the ambient gas. This ambient gas need not be only air, it can be air plus some products of combustion also, that may be hotter. Now when these dust particles mix with this, like smoke, soot particles are mixed with hot gases. These dust particles, which are fuel sources, are mixed with the hot gases, and form a cloud of fine particles which is premixed. Now here is a premixed particle plus gas. In premixed flames, it is only premixed fuel plus oxygen or R. Okay, the lift and entrainment of dust particles into the cloud depends upon the thickness of the deposit layer, viscosity, moisture content, shear stress, and material properties. But anyway, what we are trying to say is, based upon the circumstances, this is possible when fugitive dust accumulate over surfaces and there is a relative flow over this dust layer. The dust can lift and get entrained into the gas flow and mix thoroughly with them. Now, the cloud dynamics. Cloud is what? Cloud is dust plus gas. It has some dynamics. That is, for example, when it flows, when the dust flows along with the gas, the important features are seen in the movement of the cloud. That depends upon the nature of the gas medium, then the particle, dust particle itself, temperature, oxygen concentration, and level of turbulence. Now, combustion, or you can say flame propagation at subsonic speed, deflagration of dust particle in cloud depends upon basically the pyrolysis time. Chemical reaction rate, that is normally faster, but when you have dust particles, the homogeneous chemical reaction will not be much affected, but the heterogeneous reaction rate will still depend upon the nature of the dust what we have and the flame thickness, etc. Okay, so dust ignition, its transport along with gaseous medium forming clouds and cloud dynamics, then the deflagration or the way the cloud burns are the important features. Now, when if it is a cloud forms within a confinement, then the size and material of the construction also will affect the dust combustion. So, let us now see something about dust flame deflagration. So, here you can see that there is a dust layer and there is some flame which is coming into this dust layer, and the dust is lifted and entrained into this particular burnt gases. So, it may have some excess oxygen also. Now, several factors affect this: thickness of the dust, material properties, shear stress, moisture, okay, and the velocity of the unburnt gas VU. Now, coming to the confinement, construction type of the confinement, okay, smooth surfaces, rough surfaces, etc. Then partial volume explosion that can be handled by the implosion. That means whether there is any pressure build-up as the combustion takes place, etc. Then if you come to the flame zone, basically the chemical reaction time, gasification or the pyrolysis time, and the flame thickness are the factors. Now, particle, when this is dust layer and the particle is formed due to the entrainment of the dust layer into the gas, the particle size will affect the cloud formation, density, chemical composition, and pyrolysis temperature, because pyrolysis being the main thing. So, this chart gives the factors affecting the dust combustion. Now, let us see some modes, like in the gaseous flame, non-premixed, premixed, partially premixed. These are modes of combustion, correct. Now, here, since the burning of dust cloud involves heating of the particles, first sensible heating, okay, from the room temperature to the pyrolysis temperature. Then volatiles are released after sensible heating. So, volatile will mix with the volatile or what fuel gases mix with the ambient air, and if it is a charring, so the combustion of the ambient air and the volatile fuels that will occur. Then char combustion in the case of charring dust. and this flame etc. causing ignition of the unburned mixture. These are the basic steps. Now, in a cloud, there will be several dust particles. Okay, several dust particles. I'm just taking some small volume of the cloud. There is a concentration of the cloud dust here, dust concentration. Okay, so based upon dust concentration, there are two modes of combustion which can be seen as reported by Sun et al. These are the two things schematically it is shown. First one is the cloud as dust particles which are basically heated up faster and volatiles are released from the surface, ambient air enters and there is a diffusion flame which is formed, diffusion flame. And this flame heats up and ignites the neighboring dust particle and this is the propagation. So, development of the combustion region is propagated by subsequent ignition of the dust particles. Now, other scenario is there is a dust particle, a diffusion flame forms over this, but volatiles are released by all the dust particles, so a premix flame forms and the premix flame goes and interacts with the dust particles further available. So, these are the two modes and this is based upon the concentration. If the concentration is low, this is going to happen. If the concentration is high, this may happen because the heat up of several dust particles in higher concentration will lead to more volatile production. So, in the first mode, particles have individual diffusion flames, partial premixing of volatile in the air occurs and other particles are ignited subsequently. In the second mode, a premix flame is also present. These are the two modes. Now, we will see some features of the dust flames where the earliest work was done by Nusselt in 1924 and Eskov in 2003 is a recent, more recent one. Okay, basically different configurations of dust flames have been analyzed in the literature. So, one of the differences, see if you take a premix gas flame, mixture of dust and oxidizer, okay, here a gas fuel plus gaseous oxidizer like air is involved. But if you take a mixture of dust and oxidizer, say dust and air, coal dust and air, then we are basically going into multi-phase flow. That is the problem which was seen in conducting experiments as well as numerical modeling. Now, basically what happens is if you take a coal particle, if it becomes hotter, hot particle say 900 degrees centigrade, then radiation heat transfer also plays an important role in these heterogeneous flames. Do you understand? That is the difference. In the premix flame, only the gaseous participant media is there. Here some solids also are participating, that will lead to increase in the radiation heat transfer. Like in soot particle, soot radiation is going to be increased, no, when the soot production is increased, similar to that. So, now a premix dust and air mixture may not be mixed at microscopic level or molecular level as in the premix gas flame, that molecular level mixing is there, but here it may not be. So, this will typically result in two types of flames. One is called Nusselt flame, another is called volatile flame. Nusselt flame is heterogeneous combustion, that is a particle will have a diffusion flame over this. Okay, now fuel part comes from the surface and the oxygen comes from the ambient. But volatile flame is a homogeneous gas phase flame, which we have already seen. Now, let us see some features of volatile flame in the dust combustion. The dust particle interacts with a volatile flame. Volatile flame is a premix flame. So, a premix flame is there. A dust particle interacts with the premix flame as it goes through the premix flame. So as the dust particle passes through this, basically it gets heated up. Okay, and further volatiles are released from the particles, and char combustion can occur because of the heating of the char to the required temperature. When the further volatile gases mix with the air, then we can see that the volatile gases can burn as a premix gas ray under three distinctive mechanisms as reported by Borden and Fletcher. Okay, so basically it is very complicated. We can see lot of regimes and understand different mechanisms in this because of the complexity. Now, for charring fuel, the devolatilization and burning of volatiles will be there, that will support the combustion of char later. Because again, first a sensibility is required to the pyrolysis temperature where the pyrolysis gases are released. Then gas phase combustion is occurring due to this volatile and air combustion. Then further heating of char to the char reaction temperature, surface reaction temperature, that is required. So there is some time lag between these two, and this has to be understood. That is, multiple time scales are involved. Now, if you take, say, non-charring material, etc., other complexities will come in. The melting, then evaporation, then directly sublimation can occur, melting, evaporation, then vapor phase burning can occur, and so on. So, again, when there is a phase change phenomena, you have to have some time scale for that. Now, if you take, say, aluminum material, aluminum dust, or iron dust, metal dust, basically, oxide forming materials they are called, because once the surface is heated up and the surface reaction take place in aluminum or iron, etc., the oxide will be formed. Then solid oxide shell will be formed over the surface, and the operation now should occur through this shell, and the combustion of this vapor should occur outside the shell. That means there is one more resistive coating which is coming on due to the oxide formation. So these are the complexities. Now 4 zones are observed: ambient zone, preheat zone, reaction zone, and convection zone, as typically in a premix flame. So yeah, if you see Rockwell and Rengwala from WPI, they have investigated the dust flames and given out several criteria. Here it is very complicated to understand this, but what are the possible criteria are given here. The main things to remember is basically there is an equivalence ratio which is called phi u. Okay, now what is phi u? What is the equivalence ratio? Basically the air fuel ratio stoichiometric divided by the air fuel ratio actual. So based upon the air availability for the total solid fuel, I can come up with one equivalence ratio by u. Now another equivalence ratio which is called phi g, which is the equivalence ratio based upon the volatile gases which are evolved at the end of the preheat zone. So this gases with air can give a mixture of a certain equivalence ratio phi g. So this phi g basically changes from reaction to the convection zone based upon the burning of the solid phase. So as I told you, there are 4 zones. Ambient zone, nothing happens to the particles. So here you can see that the particle are now classified as A, B, C1 and C2, 4 classifications. And now in the A, the overall equivalence ratio is less than 1. Lean fuel, more air. Then B considers the entire range of Fu. Okay, it can be linear, richer, and stoichiometric. But the richer is considered in C, category C, where there are two categories, 1 and 2. Now, in the ambient zone, nothing, that is the coal particles or any other fuel particles, are in unburnt temperature Tu. Then in the preheat zone, it slowly heated up, and the reaction zone, which is very small, it burns. Then again it goes to the convection zone, where it reaches some temperature. That's it. Now, if you take the lean fuel category A, the particles number of the particle concentration is very less. So what happens is the particle goes and burns within the flame zone. Nothing comes out. Okay, now if you go to the B, the particles burn, but some particles can escape and go out here. So you can see here burning particles in the convection zone. There will be some particles which are burning still. Maybe a char burning, or a particle which is burning with a diffusion flame, etc. That will occur in this. That is the category B. Now, if you go to rich, what happens? The heat transfer may be such that all the particles are pyrolyzed when it reaches this, but the equivalence ratio in the convection zone is greater than 1. But in these two cases, you can see that the gas equivalence ratio is less than 1. Here there is no gas at all coming, everything is done, only hot gas comes out. In this case, some particles are there, but the gas equivalence ratio is lean. That means more oxygen is available for this to burn. In this case, in these two cases, in the first case, there is a possibility that pyrolysis is complete due to the heat transfer, but the pyrolysis gases does not have enough oxygen to burn, so a fuel rich gas come out. In the fourth case, or C2, you can see that particles also come out. No oxygen is available for burning the particles as well as the gas. So gas equivalence ratio is greater than 1. And here you can see this, the particles are vaporizing, not burning, because there is no enough oxygen to burn here. So there are several scenarios. Do you understand? So this is explained here. Okay, now if you go to this particular zone, preheat zone, how the volatile cracking, volatile coming out, etc. is explained, and how the heat transfer is given, etc. So they are only schematic, and so basically the sensible heating is done in preheat zone. Then volatile combustion or part of the solid combustion can occur in the reaction zone. A convection zone, based upon the concentrations, there are typical variations. So this is exhibited in this chart, which was thoroughly prepared by Rockwell and Rangwala. Now, the flame structure, whenever you do any analysis, the flame structure is what is important. So based upon the categories A, B, C1 and C2, we have several structures to discuss. See, you have to remember this chart also. As the particle goes into these zones, the particle actually is consumed in the category A. So if you see this, there is the concentration of this, basically here solid concentration decreases to 0 within the reaction zone in the category A. There is no solid going to the reaction, beyond the reaction zone. Okay, then here the heat release rate, this thick solid, this is like this, heat release rate reaches the maximum and drops. Then temperature increases in the reaction zone and goes. So typical structure, understanding what is happening in these things, we can draw this structure. Structure is what? Structure is when you draw the profiles of this heat release rate, temperature and concentrations. So this is concentration of fixed carbon, etc. Then we get this. You can easily understand this. So for the category A, it is very clear that no particles come out of the reaction zone. Category B, particles come out, but they are converted in the convection zone because the equivalence ratio of the gas is less than 1, lean. So, more oxygen is available, particles are converted, you can see this, particles are converted in this zone and heat is released. Now, in the C and D category, in the C, particles are fully parallelized. Then what happens is, even though the particles are fully parallelized, you can see that the temperature is constant because of there is no reaction taking place, no oxygen is available, it is a rich equivalence ratio. Then if you go to the D, particles are also coming out, but conversion is not there for the particles. So, the structure is plotted basically considering the 4 cases. Vaporization is complete in the preheat zone, fuel burns in the reaction zone. Case B, particle burn in the convection zone also because of the oxygen availability. Case C1, only part of the gas fuel burns in the reaction zone, but further nothing is happening. Case 2 is like case 1, but O2 limiting case. Particle convert in the convection zone also, convert based upon pyrolysis, etc. Okay. So, these are the structures of this. So, the summary is, when you take dust combustion, which is happening, lot of literature says different zones, different mechanisms, etc. and different fuels are also considered. However, you will see that the exact mechanism is very complicated. We can identify some zones and create some schematics to understand the mechanism better. Basically, the dust concentration, the dust particle size, the temperatures and the material properties, what is the pyrolysis temperature, oxygen availability, etc. will dictate this. So, based upon the scenario where you have some overall equivalence ratio for the dust phi u or overall equivalence ratio for the gases, we can categorize the dust combustion into 4 zones, that is case A, case B, case C1 and case C2, and we can draw the structure for them. So, I will stop here, I will continue in the next class.